Hello there, this is Jun Cowan. I want to talk to you about Perkins Discontinuities today. I just released a paper with Bruce Hobbs recently about Perkins Discontinuities. They look a bit like this. So you have a discontinuity, a fracture or fault, and you have high grade mineralization on one side and you have lower grade mineralization or no mineralization on the other side of this discontinuity. Now, if you see this type of asymmetrical mineralization, then I named it Perkins discontinuity from the person who described it, which was Bill Perkins. You can figure out the mineralization timing from this by just looking at this. It had to be after the fracture formation. This is a fracture that didn't displace much. These are the terminations in yellow circles. And you can see that the mineralization has to be fairly late after those fractures. Now, this is another illustration here from Lindgren's textbook in 1933. It gives an example of pyrite mineralization. You can see that it goes right across these fractures. These are apparent displacements. They're not actually displacements at all. It's just that you had one-sided mineralization on one side of this fracture. And same here, there's no mineralization on this side, only on this side, and the lamination goes right through. You can trace these laminations. So there's no displacement involved across these fractures, so mineralization is asymmetrical. Now, what we do in this paper is describe this type of situation in gold deposits, specifically in folded situations. So something like this. You might have an earlier fold and you have a fracture going through it and you have mineralization on one side. That indicates that the mineralization had to be after the folding and after the fracturing. So we're looking for this type of mineralization, and you can find that. Here you go, there's another diagram here. This is a folded unit, mineralization in yellow, and you have these two Perkins discontinuities on either side. These are fractures, and mineralization is hemmed in between those fractures. Okay, so what you can find out is that if you analyze the bedding of this unit, it plunges at 10 degrees to 160, for example here. These are the bedding readings. But if you analyze the fractures themselves, they have a different symmetry. So that's indicated by the green arrow. The intersection line, basically, of these two fractures is parallel to the green line. Whereas the plunge of the fold system, as indicated by this folded unit that's mineralized, is indicated by axis 1, which is colored in red. So you have two different axes representing two different structural events. And the mineralization is after axis 2 event. So this is a Stereonet of these fractures, these Perkins discontinuities, plotted in a Stereonet. So the best examples of these Perkins discontinuities are found in Ballarat East. So there's Ballarat, there's Victoria over here, and this is a long section of the deposit, and this is looking down. And these white lines are the traces of these what's called cross courses that go right across the train of folds. So these are fold axes in green and red. So this is a particular fold axis that you can follow all the way along. And as you can see, when they cross these cross courses, or they're fractures, basically, fractures and faults, there's hardly any movement across them. So, yeah, there aren't too many big displacements, maybe this one here, but that's about it. There's very little displacements across these cross courses that go right across the tectonic trend. But if you look at the grade distribution, if you look at the grades compartmentalized between these cross courses, you have high grade panels like this, and you have very low grade panels You have medium grade panels and then high grade, and they alternate from high to low, high to low. So looking at it sideways, you can see a high grade panel here, there's a low grade panel here, and so forth, and these are the high grades here. So this compartmentalization of high and low grades weren't really emphasized in the literature, and this is something I believe that is really important. And in addition to that, the timing of the mineralization can be worked out by just looking at this, because we know that the folds are basically very tightly folded, and they are upright here, they go along, and then they get truncated, or they get transected, I should say. They get transected by these faults, and they compartmentalize the grade. So therefore, the grade, the mineralization of the gold has to be after these fractures. So it has to be post-folding and also post-fracture, because these fractures are planar, they're not folded. So this is actually a model example of these cross courses and how they end up creating Perkins discontinuities that have asymmetrical mineralization on one side. Now, this paper that I've written with Bruce covers a whole bunch of gold deposits. These things are present in gold. If you look for them, you'll find them. But we wanted to just write a paper on gold first, and then our next paper will be on sulfides, because these structures are in sulfides, and you can see them in many illustrations and in the literature. And I'll show an example here. I'll show an example of a VMS deposit that is listed in the USGS. El Cobre, this one here, from Cuba, okay, which was discovered in 1530. And the paper that I'm going to show you was published in the 1800s, 1856. So this is the main zone here of mineralization, but you can see there's a cross course that basically truncates this mineralization over here. So this type of asymmetry in mineralization is not just in gold deposits, they're in VMS deposits that are considered to be syngenetic. And yeah, I'll be writing about those. So these are some of the Stereonets from Ballarat East. These are the modeled bedding surfaces, and I've just converted them into plates so I can actually plot them in a Stereonet. So this basically trends to 008. Axial plane's the same. There are west dipping faults that cut across that are dipping at about 45 degrees towards the west, and they tell the same story. These are the gold grades, and this is my gold LVA data. That's I can determine the gold foliation and the lineation. This is the lineation here from the drilling data, and I plot these, and they are identical to basically what you see. That's modeled by the mine geologists, and these are the LVA data. LVA, same, but what's significantly different are these cross courses. If you plot the poles, the cross courses, and if you calculate the eigenvector, the rotation axis in this case is actually vertical. So these are completely different fractures. They don't have the same symmetry, rotation symmetry, as the bedding or the gold continuity. It's actually right angles to it. So this is what I want to show you in the field. So the question is this: what do these Perkins discontinuity or these cross courses look like in the field? So I went into the field with Derek Shaw and Richard Blewett last year in Bermagui. We looked for these features. So that's what I want to show you today. They're quite unremarkable. they're not as obvious as other features that you'd measure in the field, but yeah, it's a demonstration of what they look like.
So Jun, what we were talking about is you look at this vein area here,
Yeah.
and you can basically walk out its boundaries, which is along here, over here, around here, and then in here somewhere,
Yeah.
and then like that, and it sort of continues then linear fashion there and over here. But it's got this really strong boundary here that we're still thinking about what that means.
See? You can see it here. That thing going across there.
Yes, yes.
That thing
Yes.
going across there. So
These are these branches.
yeah,
Yeah.
go right across. In fact, you can see the bedding deflection in it at a very high altitude, see?
Yeah.
Okay, I'll pause for a moment there and I'll show you where we're standing. We're standing about here. This is a three-dimensional model of the Point Dixon area of Bermagui. This is where I've flown the drone and created a model so we can actually take a look at it a bit. We can zoom out and so forth. So the tectonic grain is running about 020. This is the north at the moment here. And so we're standing right about here and we're discussing this discontinuity here. Derek has outlined this area here that has more veins than the rest of the rocks. So it's sandwiched between bedding planes that are variously dipping, but also these transecting faults. So these will be the equivalent of the cross-course faults that I've mentioned earlier from Ballarat East. So if you zoom back and look at it, this is the tectonic grain. That is consistent strikes 020 or thereabouts, okay? And these are the things going across. So these are the things that we are looking for.
Is that us?
Yeah.
Yes.
Okay. Hang on. We need some more special
glasses. See this, You have several of these, see?
Yeah.
And there's another one over here.
Oh, that's beautiful. That'd be worth looking at over there.
Yeah.
So where are we? Sorry?
We're right here.
So
So
just
we're
a smaller
sitting on
one.
that
There's
one.
two. One there, one
There's
there. Bigger
one there, one
this
there,
is more
one
an
there.
intermediate one.
And I can show you the biggest one is over here.
It's going inland.
This
isn't it?
one.
Far out. Look at that. It goes
Yes.
cuts
One
right
here.
through. It goes
Yeah.
even through the bloody vegetation.
Okay, so I've moved the drone so that it's just down here a bit. You can see the nice folding in here. That's what we're looking at now, and you can actually sort of see it branching off like this. You can see it branching off like this. There's another branch coming across this way. There's another one over here, but you know, you can actually really see it when you turn it around like this. It just goes right through, and it goes right through there. And if you come over here, you can actually sort of see it. So it's quite remarkable that you can actually sort of see these features, and it's really neat to be able to sort of do this, to be able to use a drone in the field, but also being able to actually look at these features. Okay. Yeah,
That's the
it
track.
does
Maybe
actually.
it's a very
It
light
does,
fault.
in actual fact, it comes across this way, and
Well, I wonder if it forms that cliff. It's partly.
Probably does.
you can see it. It comes out
Oh, no,
here.
But there's
Oh
one
yeah,
there. Look there.
yeah. That's the other
It's
side of it.
Look,
This one-
it's bifurcating.
Yeah, it's bifurcating.
Shit.
Yeah.
And then there's another one there. Can you go in and look at those definite things that we saw that had those strike slip offsets?
Actually, before we
Yeah.
do that, can you just go and see if I left my toothbrush on it?
Yeah. It's these ones here,
Yeah.
right here.
Yeah. Where do they fit in? There they are.
Yeah.
So are they parallel? Are they the same set? I didn't measure them.
Yeah.
Yeah, they
They're
are. They're just,
basically.
You're just running
I'll
all the way
just
through.
run it parallel to that line. Okay, I've zoomed up on the same area and I've rotated the screen. So you can see these fractures, these rather sort of minor looking fractures that don't do a lot. But they're actually, if you zoom back, they are actually parallel to these things. That's why I orientated everything so that the bottom of the screen is actually parallel to these features. Now, the reason that these things are important, I believe, in terms of compartmentalizing mineralization, is that they're not all that prominent. If you saw these in drill core, you would probably record them, but you wouldn't think they're all that remarkable. But they just happen to be parallel to these massive ones, these large ones. So I would say these are the cross courses that you actually see in the drives at Ballarat East. And these will be the minor features that you would probably find. The important point about these things here is that at the Hale gold deposit in the States that we describe in our paper, there are some grade boundaries that are not marked by dikes. So in Hale, these things are actually infilled by younger dikes. But there are grade boundaries that parallel minor features. Like you can't actually sort of see any dikes. They are most likely these sort of very sort of fine fractures that have very little displacement. You can see the apparent displacements here, like for example right here, but they're quite unremarkable actually. Yeah. Oh, sorry, I'll go up.
They look like the same sort of set.
Yeah.
Yeah.
See? Runs along the...
So that's interesting.
See, it's what
and they do bifurcate.
Yeah, they do. And I was wondering whether these black stuff, this manganese alteration, is hemmed in by one of these things. I don't know.
I've always thought it was
take
a
a
more
look at it.
superficial thing, like it's a weathering.
Yeah, but it could be like if they represent something
Some
that
primary
pre-existed,
that's
then that might mean
reworked
something.
by the later weathering.
Yeah.
You
So-
see them all over the Yilgarn, and you even get it on top of the soil in some places.
Yeah.
And I don't understand the genesis of it at all. When I first saw it decades ago, I thought, oh, it's something that forms at the unconformity between the soil and the rock, but it might well be, but that doesn't necessarily explain all of it. So
This is useful to have a drone, eh?
very.
In the field.
Not convinced
Because
of the utility of having a microphone that records everything I say, though.
Okay, for a moment there we were talking about these black bits here, which are apparently manganese. I'm really not sure, but what I was wondering was whether these things had a similar sort of effect as the compartmentalization of gold that you see between these transverse fractures in Ballarat East. So you have these black patches here, which are obviously superficial, but who knows? I mean, does it reflect something of the host rock, the geochemical character of the host rock that makes it go black in certain areas and not in other areas?
I'm struggling to reconcile the timing differences.
Of the veins?
These veins look really deformed, Boudinot, ripped apart, disaggregated. They're different to the planar guys that are cutting across things we've been talking about earlier.
Yeah.
To me, when you go in and look at that outcrop over there underneath the fold, you can see it going under the fold. It's folded, right? So it's pre-F2. There's melange veins.
Those ones, you
Yeah.
reckon?
Yeah.
I think that whole thing where you're pointing to at the bottom of that is you could define it as one continuous unit that goes all the way through here, along there and out there somewhere. But why it's like that, I don't know.
And it may
It looks
transgress. It may transgress actual stratigraphy in the folds, but as overall it's folded. So it's pre-F2, this main asymmetric folding that we're seeing in this outcrop is what I'm thinking. The alternative, I suppose, is you've got that fold geometry, and for some reason you're placing veins into these zones, which is, I think that's your hypothesis.
I think.
But I just worry about the nature of these veins. I don't understand why you'd have these sort of disaggregated blobby bits that are really strung out. They're strongly foliated. I mean, this is high strain, some of this.
I still can't get past the fact that that doesn't continue past where I'm standing. I still don't get that bit.
Okay, so there's a lot of things that are mysterious, and we go on to debate all sorts of details on the outcrop about the nature of the veins and so forth. There is no doubt that there's early set of veins that have been folded by in the first phase of folding as well as the second. So there's several generations of veins here, and which you can't see in the model. But one thing you can do with the model like this is that you can actually sort of quickly characterize the structural nature of some of the features that you can actually see here. For example, you can actually see the bedding quite well. You can't see the cleavage well at all, but you can actually sort of see folds. So what I want to do here is to demonstrate quickly what you can do with by digitizing some of these features. So there are two sets, okay, that I want to characterize. The bedding that you can actually see, that from that we'll be able to get the tectonic trend from the bedding data. So if you look down on it, it's trending about 020, something like that, that sort of trend. And then you have these transverse features, which are the cross-course equivalent, and I can digitize those. So I'll do that now quickly and then plot those up separately. Okay, so I'll digitize some bedding readings. You have to make sure that you are glancing in the plane of the bedding when you are digitizing this. This is very important to do that. That's overturned, by the way. That's that pale color there. Well, although I actually don't know the which way's up here. I'm just assuming that this way's up. See that this light colored. So you can go around and sort of trace it around and digitize it that way. And you can see a trace of that as well. So you can actually sort of digitize it like this. So I'm digitizing it so that I'm getting the same direction as way up. I'm making an assumption that this is way up to the left, which is to the east. Right, I think I've got enough here. So I can save this. Okay, so this is what I've digitized. And turning on the Stereonet looks like this. So great circle would fit along there, okay? Now, let's look at this with eigenvectors. So this is what the eigenvectors look like. E1 would be where all the clusters are for the poles of the bedding. E2 would be 90 degrees from that along the great circle. So that's where it is right there. And the third eigenvector would be right angles to both of them. So that would be the pole of the great circle that fits along here. Now, what most people don't realize is that I've been using a rotated grid system for quite a while now. Like for example here, these have rotated grids, and what these rotated grids actually mean is simply rotating the equator, this equator grid. This is a meridional north-south grid that you see in any Stereonet software. That equator becomes the great circle, basically. So the great circle is the equator of a non-meridional grid. That's what it is. Okay, so I'll show you that. So that's what it looks like with the meridional grid rotated so that the equator lies along as the great circle that goes right across the main poles of the bedding. And then right angles to that great circle is the axis of rotation. So these are poles of the bedding, but if you look at the great circles, if each of these are displayed as planes, that's what it looks like, plotted as planes. So they all intersect here at the axis of rotation, and this is why it's called axis rotation, is because, you know, if you take a plane that goes through this axis and rotate it, and you'll get that sort of distribution here. So yeah, so that's the axis of rotation. So another interesting thing about this plot is that you can actually sort of highlight how much of a departure you have from perfect cylindricity, which is represented by this great circle here. So here we're departing 5, 10, 15 degrees away from the cylindrical solution here. I estimated the tectonic strike to be around 020. It's the strike of this would indicate about 028, so pretty close. The plunge of the system is actually closer to 020, but plunging the opposite direction. Okay, now I'm going to digitize the transecting fractures or faults. So these are the features here. These are the bedding readings that just grayed out. They're not active anymore. So I'm going to digitize these. See how I am glancing in the plane, into the plane? So when I'm looking at the other side, I can do the same. This one, the red is to the north. I'll just make it consistent. That basically tells you the polarity. That's the positive side, the red. The negative side is in the blue. So in Leapfrog is exactly the same. So I'll keep on digitizing these and get a set of measurements. See how these are quite, not all of them are steep. Interesting. I guess that should do. Yeah, these things are not obvious in the field. I mean, in the field, the most obvious things are obviously bedding and cleavage and fold closures and so forth. So these features that cross-cut the tectonic grain here, you know, when I was an undergrad and we were mapping this area, we didn't even take notice of these things. We noticed that some of them were filled up with dikes, lake dikes, but they're not that obvious. It's not something that we measured. So you know, using a drone and a model like this, it actually allows you to sort of see things that you don't normally see in the field, just because of the scale of observation is completely different. Okay, so the cross courses that the fractures that I've digitized are red, and the beddings are grayed out. Okay, so what does this Stereonet of the cross course fractures look like? Okay, so these are the transverse faults plotted in the traditional meridional net that you see in most publications and textbooks, but the great circle in this case would go across this way, so the pole of rotations should be around here somewhere in the northwestern quadrant. So let's plot the eigenvectors. Okay, so these are the eigenvectors. You can see that this is the mean orientation of the fractures, and the great circle, the best fit great circle here would go like this, and this will be the axis of rotation. Remember that the axis of rotation for the bedding was down here somewhere, about 10 degrees to 198 or something like that over here. So it's completely different. It's about 90 degrees away. Okay, so let's rotate the grid so that it conforms with the eigenvectors. Okay, so this is what it looks like. So the rotation axis is plunging at 56 degrees to 323. So it's in that direction here, as opposed to the bedding down here somewhere. So I'll plot both of them at the same time. Okay, so this is both plotting the bedding, which is in red, poles, and the fractures. And if you plot the great circles, you can see that the bedding intersects down here, whereas the transverse faults intersects here, which is the rotation axis for the transverse, what I labeled as cross course. So there you go. So these are two different systems. They have an axial symmetry that's quite different. They're about 90 degrees away from each other. So the bedding sits down here, the rotation axis down here, whereas the transverse faults, the cross courses, intersect in this region here. So remember when I was saying, talking about this diagram here, you can see the folded unit that is plunging towards the south in this case. That's 10 degrees to 060. And the Bermagui folds are like this. It's plunging towards the south. I didn't get into the complicated story about F2s and F1s and so forth. But they are coaxial anyway, so it wouldn't make too much difference. Okay, so the cross-cutting faults have a different symmetry, and like this example here has a steep axis here. In our case, it was plunging towards the northwest, something like that. So you can tell, you can measure these things. They have two different axes. This is axis 1 that's parallel to the fold axis. Axis 2 is the intersection of all the transecting faults. So you need to determine these things in order to figure out where the boundary of the gold mineralization is. So hopefully this this video has taught you a few things. Basically, I wanted to explain what our paper was all about. It's all about identifying these two different sets of symmetries in your rocks. They will control the mineralization pattern, especially the second fabric that transects the folds. Gold mineralization will continue along the fold axis for a while, but then it gets terminated, and it gets terminated by these cross courses, and you get these asymmetric mineralization across these fractures. So that's really important to realize. Thank you. So if you are interested in applied structural geology, Brett Davis and I are running a workshop from the 1st to the 5th of October 2025, just after the SCG conference. So we're going to have this in Perth. Here's the two Ronnies here. And yeah, we're going to be running the course. Brett's going to be doing the inside out technique, whereas, you know, looking at rocks, looking at outcrop, interpreting it. I'm doing the reverse. So I'm doing the sort of things that I just showed you just then, using models. And also we're going to progress into interpreting grade data. So grade data can be analyzed just like outcrops. We use the same techniques, but we interpret grade. And I'll teach you how to do that. And it's something that I think every applied geologist working in the mining industry should really know about. So yeah, sign up for it. I'll leave a QR code or a link. So please contact us if you are interested. You might as well come down to Perth if you're coming down to Brisbane for the SCG. See you then.